Welcome back to the course in Nuclear Medicine Physics. Today we're looking at the design of PET detectors. In particular, we'll look at different types of scintillators used in PET imaging. We'll compare different types of materials and talk about why some are better than others in certain ways for the detection of the types of photons emitted in PET imaging.
Okay, so in this lecture, we're going to take a step forward and talk about some of the detection and design considerations in PET imaging. So we've had previous lectures where we've talked about scintillation and scintillators, which are very important in nuclear medicine. So you could look at some of those for more detailed aspects of them, but just today we will focus more on just a very quick overview and then focus more on the PET side of things. So what's a scintillator? When you have incoming gamma rays, um, that are absorbed in a scintillator, they lose their energy in the scintillator through the photoelectric or Compton mechanisms. Pair production is possible too, but that again, as we've said before, that only happens if your energy is more than 2 times 511 keV, which is not the case in PET. So the energy is being lost either through photoelectric or Compton mechanisms. And then the electrons that are generated because of these end up creating excitations in the scintillator molecules. These crystals, the molecules that they have, they're excited. So these are molecular excitations. It's analogous to atomic excitation, but very different. So kind of like, how in atomic excitation, you may get an excitation and then it comes back to ground state and then emits and glows and emits associated X-rays. Here too, you've got molecular excitations, which is a different phenomena than atomic excitations. But then once you come back to the ground state, there's scintillation photons that are typical in the optical, visible light domain. And then those scintillations, so incoming photon absorbed, scintillators are produced, many of them, thousands of them produced for a single gamma ray coming in. And then you enter this PMT. We've talked about this before. You have a photocathode. So then an electron is created here because of the incoming scintillations, creating that knocking off that electron. And then the electron ends up being amplified through these diodes, and you get an electric pulse at the end. So we talked about these. But there's a large number of different scintillation crystals that exist for different applications. What really defines the value and the use of them for our applications is their density and atomic number. You want these numbers to be large because you want high stopping power. And this is especially the case for PET imaging because you've got 511 keV. These are highly energetic gamma rays coming in. You want something that is dense and has a high effective atomic number to stop that light. But you don't just want to stop light, gamma rays. You also want to produce scintillation light. So it has to be the right right material. And you don't want the decay time, for example, to be too long because then it takes forever to process and then there's dead time associated with it. So there's a number of considerations, cost being one. One reason PET scanners are more expensive than single photon, let's say SPECT cameras is really this, because you're being pushed to use different kinds of scintillators than sodium iodide. So you need high density, you need high Z or high Z, and so-called inorganic scintillation crystals meet this criteria. There's different kinds of scintillation crystals. There's organic ones, which we're not talking about in this lecture. Carlos has talked about solution-based or liquid scintillators, etc. But for a PET scanner, for example, so-called inorganic scintillation crystals meet these criteria. Their densities are good, and they are suitable for absorbing penetrating radiation. So we've shown this table a number of times before, but sodium iodide you sort of see for PET scintillators, especially BGO was one of the exciting ones early on, and nowadays many people are using, many vendors are using LSO, many researchers are using LSO. You see that it's more dense. The effective Z or Z is somewhat higher. and conversion efficiency. So sodium iodide is very good in conversion efficiency. Once it absorbs, it really produces significant scintillation. So you can sort of see that even though BGA was not the best, LSO comes close. So LSO is very nice. It stops, it's very effective at stopping incoming gamma radiation and also in converting it into scintillation. And you can sort of see also that it has a very good small decay time. And that means that there's less dead time happening because it takes you a small amount of time to process one gamma ray, then you're ready for the next gamma ray and then the next gamma ray. In the early years of PET, we had some crystals, scintillators that were used, cesium fluoride, for example. These were actually very fast, and they led to the so-called time of flight PET, which we will talk about in a follow-up lecture. But they were not very effective in terms of light production, light output, conversion efficiency. So even though they were super fast, they were not, very sensitive at the end of the day. So people have stopped using those. And people even put time of flight aside, but then now they've come back and revisited it in the context of LSO. We will talk about all those. So again, light output is very important, and you want something that has a high light output, not just absorbing effectively, but also producing high scintillation, photon yield. And the wavelength should be matched to the sensitivity of, for example, the PMT that is going to amplify. So matching the wavelength to the PMT that goes at the back of it is important, some design considerations. So looking at the decay time, and it's not just the decay time that's important, but also the rise time that's important. So here's a scintillation event where you've got that molecular excitation happening. You're having a rise time, something starting to happen, and then as it glows and as it gets rid of the scintillation photons and returns to ground state, you see this kind of a decline here. So there's a rise time, and the rise time is very important because you want to know when the event came in, and the decay time is important because you don't want this to take forever to process. So you want fast rise time in the scintillator. That's important for narrowing down the coincidence timing window, because if you are so uncertain about when the event came in, your coincidence window becomes bigger and bigger. So you could be like collecting events, so-called random coincidences, events that are happening at the same time, and they're being detected at the same time, and the camera is getting confused. The camera is saying, whoa, I just got these events, but they're actually events from photons or gamma rays from different events. It's just that the coincidence timing window is so wide that it's accepting, events that are actually not originating from the same source. So we will talk about random coincidences in a future lecture. Hang in there. Also, as your coincidence timing window becomes better and better, you can do better and better time of flight. Certain terms that we will actually really go over later. And then, as I've said a couple of times, you want fast decay time. Because if the decay time takes forever, you're going to get a significant dead time. Okay. So here's an example of decreasing crystal size per PMT. What does that mean? One of the main, and this is very, very analogous to angular logic. It is a form of angular logic that we talked about in the context of single photon imaging in the past. Well, it used to be that early on you had a scintillator, and then it was paired to a PMT. But then to make the scintillator smaller and smaller, you have to make the PMT smaller and smaller, and that's going to lead to complications. So it's going to make your scanners very expensive to design very, very small PMTs all over. But there was this really innovation that happened decades ago, very analogous, very consistent, same way of thinking of for angular logic actually. So so you would take a scintillator block, you would cut through it, and you could fit these spaces with reflective material that reflects scintillation light to maintain it within this space. But then using angular logic, as we've talked about, so if you have an event, let's say gamma ray comes here. This gamma ray results in scintillation photons. These scintillation photons, some of them end up here, some of them end up going here, some here, some here. And by angular logic averaging, you can actually narrow down where it came from, because now you're using the signal not just from one PMT, but from, for example, two PMTs here. There's actually four, because it's in this angle and in that angle. Okay, so here's an example of that shown here. This is, for example, an 8x8 cut through like a BGO crystal block. You've got four PMTs at the back, and by using angular logic and angular averaging, you sort of know, okay, so if an event, for example, comes from here, it's going to give you a lot more scintillation light here than in these ones, and so by averaging, you will be able to narrow it down. Showing you the exact same thing here. Then you take these blocks, right? Let's say an 8x8 or 12x12, 13x13 block of crystals. Then you could insert them, for example, like a cylinder in a cylindrical design here that you will. This is a circle, but you go like multiple rings. So that gives you a cylindrical design. There have been different kinds of designs. This is the most popular, but you could also have partial ring cameras where maybe they rotate, not popular. And what you have is also sometimes you have flat panels. Flat panels are also kind of interesting to design. You may have some gaps and empty space here, so your image reconstruction might have to fill this up because you may not fully cover this area. That's okay. Again, another example, you could have a design like this, partial ring. It may rotate, it may not even rotate. Like in mammography, you could have the breast compressed between two parallel. So this is positron emission mammography, PEM, where you could compress the breast between two planes. You will not have full angular coverage, so you're not going to get, full tomography, but you could at least get some depth resolution, for example, right? And you could have, So basically, you're having really different kinds of designs that might be happening, but this has been the most popular one here. So here are some questions. The first three are actually from my previous lecture, but these next are from lecture right now. Now, there's, people like you, physicists, engineers, have made a tremendous difference in this area. I just want to share one example with you. A really interesting and influential study by my fantastic colleague, Dr. Dan Kattermas, that was performed. But let me first give you the context here. There's a comparison of PET imaging platforms that occurred, early, soon after year 2000, because around that time, there was a lot of clinical utility and reimbursement for PET that was being experienced. So manufacturers were rushing towards building different kinds of scanner models. People had so many different ideas about how to build systems. So some people built dedicated high resolution tomographs, which is what we have today. But also others were thinking about other designs. Some were saying maybe we can just continue to use sodium iodide that is used for gamma ray, but just really build, surround the patient with it, not just like a 2 or 3 head, like a single photon emission, but really surround the patient like we do in PET. But instead of using BGO, we would use sodium iodide, so less expensive, but really dedicated. Or let's just take existing, gamma cameras, add a coincidence detection system, just use 2 heads, 3 heads, see how it works out. It will be less expensive, but it might be very good. So you had a cost ranging from, let's say, a few hundreds of thousands of dollars to $2-3 million. And there was a need for assessment of image quality. Okay, and we will have a lecture in the future by Dr. Abhinav Jha, who's going to talk about task-based image assessment. Okay, and assessment of image quality for specific tasks. That's a very important topic. So my fantastic colleague, Dr. Dan Kattermas, he took 7 scanners, as I mentioned, 3 dedicated BGO systems, more expensive, 1 intermediate price, where surrounding the patient with sodium iodide, and 3 sort of gamma cameras systems with 2 or 3 heads, but having added the coincidence detection system. Not very high sensitivity, but definitely far less expensive. So he started looking at those, and here's a number of crystals, for example, in the 3. So you see about 12,000 these are numbers, thousands, tens of thousands of crystals in dedicated PET scanners. Whereas here, you're thinking in terms of heads, like gamma camera heads, right? You're thinking in terms of sodium iodide. We don't think of it in terms of individual cut crystals. We think of it in terms of how many, flat heads do we have. So here they had high sensitivity, and yeah, so one of the, the most expensive parts of a PET scanner end up being the detector part. So the scintillators and the PMTs, you have so many, you have dense scintillators, and you have the PMTs that are associated with them. So that makes a PET scanner expensive in this design. Okay, so and here you see the sensitivities for these ones are quite lower because they were just using like 2 or 3 heads, like a typical gamma camera. Okay, less expensive, but is that okay? So he ended up using this anthropomorphic body phantom, which years later he ended up actually passing to our lab just 3 nights ago. We were doing an experiment on this. He ended up inserting many lesions. Sodium 22 is positron emitting, and it behaves quite similarly to fluorine 18 actually in terms of positron range. It's just that it's far more long-lived, so you could house these sources and use them in different experiments. And then here are some examples of the reconstructions that he got on the 7. This is just the lesions, but on the 7 different anthropomorphic realistic phantom studies. You can sort of see that the image is sort of degrading. And here's an example again of some of them that you see here of a 7 millimeter diameter lesion in some of these cameras. But the point is, and he did some observer studies, and Dr. Jal will talk about this in a future lecture, but the point is the fraction of lesions that were properly, correctly localized within a reasonable radius, because if the radius becomes wider and wider and wider, then localization becomes meaningless. You want to localize within a reasonable, correct range, right? So if you're within 10 pixels, this is acceptable, for example. But the point is, the dedicated cameras, the advanced sophisticated cameras had significantly improved localization. And so there was demonstrated highly significant differences in lesion detection performance between each class of PET detectors, whether you're doing the far less expensive gamma cameras versus the more dedicated sodium iodide based scanners versus high resolution BGO. But the point is, he demonstrated that these kinds of cameras, the dedicated BGO based, moving beyond sodium iodide kind of cameras, had significantly improved detection performance. So because of that, this had a long and lasting input, and the vendors stopped, using more conventional designs. They said, no, PET is a kind of a different ballgame. We got to move on to different kinds of scintillators. So that's why the vast majority, almost all vendors, started really moving away from those kind of designs and looking at these kind of designs. So high resolution, dedicated, BGO based, and later LSO, and even better crystal based PET tomographs became the accepted standard. And purchases of the less expensive but limited image quality systems fell dramatically in the following years. Okay, so this is an example of somebody like yourself doing very meticulous, valuable studies, really convincing the vendors, teaching them this is the way to go, and as a result, I think making a tremendous difference. And as I've told him, told Dan, I say that Dan, I have no doubt that your work has led to lives being saved because of what you did. And this is something that has to we have to keep revisiting this idea, right? Because now you have more advanced image reconstruction methods. Maybe you can revisit the idea of partial ring PET cameras, because you could do, advanced compressed sensing based or AI based image reconstruction, blah, 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 blah. The point is, as new reconstruction algorithms emerge, as new systems emerge, there's a continuous need for continuous assessment of these systems and coming up with new and interesting designs. So besides what we just mentioned, have PET scanners since then, since the vendors in the early 2000s switched to, let's say, BGO-based and later LSO-based PET scanners, dedicated high-resolution PET scanners, has there been further advancements? And the answer is a definite yes. Things like time-of-flight PET, 3D PET acquisition, multimodality imaging, combining PET with CT or with MRI, and moving towards longer axial field of view imaging. And this is exactly what we will talk about next.